I'm excited to present our paper entitled Replacing Rewards with Examples, Example-Based Policy Search by Recursive Classification. This is joint work with my advisors, Sergey Levin and Ruslan Solokhutinov. This project is primarily about a different way of teaching autonomous agents new tasks. As the title says, we will avoid defining reward functions and avoid providing full human demonstrations, and instead define tasks in terms of data, in terms of examples. This talk will first outline exactly what this problem is, explain our method for approaching this problem, and then discuss some results. Let's think about how we teach agents new tasks. For example, we might want to teach this robot how to knock a nail into a board. The typical RL approach is to define a reward function that tells the agent how to solve the task. For example, on this hammering task, a common reward function would look like this. There are a bunch of different terms corresponding to whether the hand has picked up the hammer and whether the hammer is near the nail, and so on. Constructing these reward functions is pretty hard. It often involves knowing not just what the task is, but how the agent is supposed to solve the task. And measuring the reward functions is also hard. It often involves adding a number of sensors to measure the position of the hammer and the nail and so on. And moreover, there are a bunch of hyperparameters, such as this 10 and this 0.01. How are users supposed to choose those? And constructing reward functions like this is really hard for users that don't know how to program. So in this paper, we're going to consider a different way of teaching robots new tasks. We're not going to provide reward functions. We're not going to provide full expert demonstrations. Instead, we're going to provide states, images, where the task is solved. For example, in this hammering task, the user provides states where the nail has been knocked into the board. Note that the user doesn't actually need to know how to control the robot to do this. The human could leave the robot entirely untouched and grab a different hammer and use that to knock the nail into the board. Or they could simply look up images on the internet of nail knocked into board. Solving this problem is important because it would make it much easier for humans to teach agents new tasks. Let's formally define this problem of learning from examples. We assume that an agent, like a computer, interacts with an environment. The agent observes observations and outputs actions. Now, in standard RL, the agent would get to observe reward functions, but as we've discussed, these reward functions are often hard to construct. So instead, the agent will get to observe these success examples. These states are provided before learning. What that means is that once the agent starts training, it never needs any human feedback to guide its learning. It's purely autonomous in that sense. Intuitively, the agent's aim is to maximize the probability of reaching success examples, or to reach states that look similar to success examples. We'll call this problem example-based control. To define this problem formally, we have to introduce a bit of notation. We will use this E variable to indicate whether the task is solved or not. So we can write the probability distribution of success examples as P of S given that the task is solved. Importantly, the agent does not know this probability distribution, and it only has a couple samples from it. Now, what we care about is the probability of solving the task at some point in the future. We will use E with the subscript T plus to indicate that the task is solved not now, but at some point in the future. Precisely, we will look at the discounted future, similar to standard reinforcement learning. Of course, the probability of solving the task at some point in the future depends on what actions you take in the future, so this probability depends on the policy pi. Our objective is to find a policy pi that maximizes this probability of future success. This is the objective for example-based control. One way of understanding example-based control is to compare it to standard reinforcement learning. Both involve the probability of something happening in the future, either receiving rewards or reaching successful states. In fact, we can express the example-based control objective as a standard RL problem with a reward function that indicates the probability of solving the task at each time step. However, we don't know how to compute this reward function. While we're given a couple examples of states that solve the task, we don't know the probability that any other state solves the task. Now, this connection suggests a sort of roundabout way of solving example-based control problems that's been used in prior work. We could first use the success examples to estimate the probability that every state solves the task, and then we could apply a standard RL algorithm to that learned reward function. But as we'll show in our experiments, this approach, while working well on simple problems, doesn't scale to more challenging tasks. The main component of our approach is a classifier. This classifier takes as input a state and an action, and predicts whether the state and action lead to future success or not. If we could learn this classifier, then we could determine which actions we should take to maximize the probability of future success. But actually training this classifier is a little bit tricky because of the data that we have. If we wanted to train this classifier using standard supervised learning, we'd have to have labels that tell you for each state action pair whether that led to future success or future failure. But let's think about the experience that the agent actually collects. Here, we visualize 3 different trials when the agent was interacting with the environment. Now, if someone told you which of those states resulted in successful outcomes versus failed outcomes, we could go back and label each state an action. It would look something like this. The green state action pairs would be given positive labels, the red state action pairs would be given negative labels, some would be given both positive and negative labels, but that's fine, just like having noisy data. And if we had this data, we could fit the classifier using a standard cross-entropy loss. While this gives us some intuition for what the classifier should learn, we don't actually have access to this sort of data. Recall that the agent receives the success examples before learning, so it does not get any feedback about whether its own trials resulted in success or failure. What data do we have? We have the success examples, which were provided before the agent started training, and the agent's own experience. We don't know whether the agent's own experience led to successful outcomes or failed outcomes. So what we'd like to do is express this cross-entropy loss in terms of the data that we actually have. To do this, we know that there is a recursive relationship between the classifier's predictions at different time steps. In particular, the probability of solving the task in the future is equal to the probability of solving the task at the next time step, plus the probability of solving the task after the next time step. This is the main idea, which allows us to re-express the same classifier objective as follows. This objective has an intuitive interpretation. The first term says that if the current state is a success example, the classifier should predict 1. The second term says that for all the unlabeled experience, the agent's prediction should depend on some function of the classifier's prediction at the next time step. Because the classifier is trained using its own predictions, we refer to this idea as recursive classification. And one very important point about this new objective is that we can compute it using the data that we actually have. You might notice that this objective looks similar to temporal difference learning. The objective function depends on the classifier's own predictions at the next time step. However, whereas standard TD learning is applied to reward functions, our method is applied directly to data. Thus, our method can be interpreted as a sort of TD learning for data. We call our resulting method Recursive Classification of Examples, or RCE for short. Now, rather than presenting the full algorithm, I just want to explain how you would actually implement RCE, because it's really simple. Let's say you start with an off-policy actor-critic RL method, such as SAC or TD3 or SVG or DDPG. The first thing you would do is change the activation function at the end of your Q function to be a sigmoid. This turns your Q function into a classifier. The second thing you would do is replace the standard TD loss that depends on reward functions with the Bellman loss, which depends on not reward functions, but success examples. In total, this would involve changing about 4 lines of code. Of course, we've also released code. Now let's see how RCE works in practice. We'll start with the hammering task we looked at before. The aim is to have the robot pick up a hammer and knock a nail into a board. The success examples are states where the nail has been knocked into the board. And note that we're not giving the agent full demonstrations. These success examples only show the desired outcome, but don't tell the robot how to pick up the hammer and how to do the hammering. Well, compared to a number of prior methods, Vice is a prior method that performs example-based control. The rest of the baselines are state-of-the-art imitation learning methods. As mentioned earlier, some of them can be interpreted as learning a reward function from the success examples and then applying reinforcement learning to that learned reward function. All methods receive exactly the same inputs, the set of success examples and the agent's experience interacting with the environment. But no method receives any sort of task reward. Now, to evaluate the methods, we'll use a reward function designed in prior work. A good agent gets a reward of about 10,000. We emphasize that this reward function is purely for evaluation and that none of the agents will get to see this reward function. And we'll plot this reward throughout the course of training. When we plot the prior methods, we see that none do exceptionally well. And this is not very surprising, as the example-based control problem is really challenging. The agent doesn't get any reward functions, no reward shaping, no demonstrations telling the agent how to solve the task. And in fact, the agent is only told what the task is, not how to solve it. In contrast, we see that our method does reliably solve this task. We attribute this success to 2 factors. First, unlike the imitation learning baselines, our method is directly trying to solve the example-based control problem. Second, unlike the prior example-based control method, Vice, our method does not require learning a separate reward function and is thus more end-to-end. Here we visualize some of the learned policies on this hammering task. The policy learned by RCE succeeds in knocking the nail into the board for most trials. The best prior method, squill, does succeed in picking up the hammer, which is really hard, but it doesn't succeed in using that hammer to knock the nail into the board. Let's look at another task. In this bin picking task, we want the agent to pick up a green block and move it into the blue bin. Now, the reward function used in prior work is really complicated. This sort of reward function is pretty typical for prior work. Here's the other half of the reward function. In contrast, we're going to try to learn to solve this task using success examples. On the right, we show some of the success examples in no particular order. Note that because we haven't provided reward shaping or demonstrations, solving this task is also really hard. Applying our method in the same baselines to this task, we see that our method is able to successfully solve this task. The best prior method, squill, is unable to make any learning progress. And we have a bunch more results in the paper. One important aspect of example-based control is that it should enable an agent to learn a general notion of success. The agent shouldn't just memorize the success examples. And this is really important for real-world tasks, where specifying every single way that an agent might solve a task will be really, really challenging. Our final experiment tests whether RCE does learn this general notion of success. To do this, we'll try to teach the agent to reach for an object, regardless of that object's size. So one success example might look like this, another might look like this, and a third might look like this. If the agent simply memorized the success examples, it wouldn't know what to do when given an object that was a different size. Applying RCE to this task, we see that it can reach for objects that are different sizes than any of those seen in the success examples. This experiment shows that RCE does learn a general notion of success, and is not simply memorizing success examples. To summarize, this paper looked at a different way of defining RL problems by replacing reward functions with examples of desired outcomes. This problem formulation may be useful to researchers who have wanted to apply RL to their problem, but have been stuck on how to define a reward function or how to measure that reward function. Because this problem area is relatively underexplored, there are likely to be many better ways of designing example-based control algorithms that work even better than RCE. Please check out the paper and poster for more information. We've released code as well as other materials on the project website. And if you're interested in chatting more about RCE or future work, please stop by the poster or get in touch. Thanks.